The expectation and variance of linear functions of random variables. Okay, so great. So let's consider two sets of random variables, x1, x2, up to xn, and then another group, y1, y2, up to yn. So you've got this collection of random variables over here. You've got n of them. They may or may not be independent. You've got these random variables over here that may or may not be independent. Let's just think about the x's first. I'll just hide these from view. These can be any random variables. And let's let a1, a2, up to an be real constants. Okay? And then also we'll have these b's, but we'll deal with the b's and the y's later on, or in just a moment. But what can we say? Well, it turns out that the expected value of the sum of the ai xi, I goes from 1 to n, this turns out to be the sum, we already knew this, of the the ai times the expected value of the xi, okay? 1 to n. So this is really convenient. For example, if you already know the distributions of these x's, maybe you can get the means really quick, and the expected value of this weighted sum is just the sum of the weighted expectations. Think of it like that. By the way, where might you encounter some sum that looks like this? Well, you could think of these x's as, say, the random demands for certain objects, like x1 is the random demand for item number 1, and x2 is the random demand for item number 2 in a day or in a week or whatever. And then maybe the a1 and a2, maybe these are the profit figures for each one. Okay, so your total profit then is going to be, the number of things you sell for item type 1 times the profit that for that item plus the demand for the next item times the profit and so forth. And maybe you want to find the mean of the total random profit, the expected total profit. Okay, would look something like this. Number 2. Maybe you're also interested in the variance of this sum. Well, turns out this can be expressed pretty nicely this way. Okay, it's the double sum. I goes from 1 to n, j goes from 1 to n, of ai times aj times the covariance of xi with xj. Okay, now this looks complicated, but it's not. It's not too bad. First of all, how many terms are in this sum? You got n times n. There are n squared terms here. Okay, right? You've got, for every value of I, j is going from 1 to n. Now, so what happens when I equals j? When I equals j. For example, if I equals 1 and j equals 1, then you've got a1 times a1 times the covariance of x1 with itself, which is the variance. Okay, and a1 times a1 is just a1 squared, right? So whenever I equals j, then this part will look like a sub I squared, and this part will just be the variance of x sub I. Okay, so I can pull out, and that's going to happen n times, right? When I can equal j when they're both equal to 1 or 2 or 3 or 4 up to n. So I could, if you want, you don't have to, but if you want to, you can pull out those terms where I equals j and express this way. It's just another way to think about it, which may or may not be convenient for whatever purposes you have there. Sub x, right? But then I still have to add those covariances, right? Plus, maybe I could write it like this, I guess. I equals 1 to n, j equals 1 to n, where I does not equal j. Okay? A sub I times a sub j times the covariance of x sub I with xj. Okay. Sorry, I went over my boundary there. Okay. So here there are n terms over here. There are n terms over here, and there are n squared minus n terms here. Okay. All right. See that? See that? See that? Yeah. Okay. And still another way you might see this expressed is like this. It's leave the first part alone. It's the sum from 1 to n of a sub I squared times the variance of x sub I plus, you might see it like this, 2 times the double sum. I goes from 1 to n minus 1. J goes from 2 up to n of a sub I, a sub j times the covariance of xij, xi times xj, sorry, xi, xj, comma, there's a comma between them, arg. So here this is the only part that's changed, right? This sum of the squared constants times the variance is still the same as it was before. You have n terms here. Over here, all we've done is noted that here you still got n squared minus n terms, but actually here, if you just look at the sum, you've got half of that many. Because it turns out, if you look back over here, you see some of these terms are going to be the same. Like when I equals 1 and j equals 2, okay, then you get a1, a2 times the covariance of x1 with x2. And then also you have the case where I equals 2 and j equals 1. And then you have a sub 2 times a sub 1 times the covariance of x2 with x1. Those two terms are the same, right? So you could just do that computation once and then multiply by 2. And that happens for every pair of terms. And look at here, we're going, I goes from 1 to n minus 1. J goes from 2 up to n, because otherwise you have overlapping there at the endpoints, and we don't need for that. We've already accounted for when I and j, when the indices are the same over here in our variance part. Okay. Oh, and so this is for sorry, I need one more stipulation here on this summation. I is less than j strictly. Okay. Oops, can't see that. There it is. This is just for I strictly less than j. Okay, so sometimes you see it written like this. I think this is the best way to remember it right here. Okay, this is the best way to remember that the variance of the sum of the weighted random variables here is it's just the double sum of you just multiply the constants times the covariance of the two and add them all up, all n squared pairs, even the duplicates. Okay, so there's one more thing that we ought to remark on here, and that is, of course, number 3. Got 1, 2, and 3. Okay, now let's think back about these y's and these b's. We haven't used these other sets of random variables and constants. Okay, maybe you could think of maybe you could think of these x's as demands in the summertime or something on a particular or demands in one certain store. Okay, over a week, and then maybe you could think of these as the demands in another store. Okay, and maybe you wonder if they have anything to do with each other. Okay, so if I'm interested in, maybe I'm interested in the covariance of the total profit at both places. Okay, which I could write like this: covariance of the sum of a sub I, x sub I goes from 1 to n, with, this would be the total profit, and in fact, I don't have to have the same number of y variables as x variables. I'm going to change this to m, okay? I'm going to change this subscript to m. Okay. It could be at one store you have a different number of items. Okay. All right. So then this would be, oops, I goes from 1 to, yeah, M, sorry. And maybe we'll give this the subscript j. And then b sub j times x sub j. Okay. Turns out this is equal to the double sum. I goes from 1 to n, j goes from 1 to m, a sub I, b sub j times the covariance. Of course, this is supposed to be a y. Arg. Okay. Yes. Covariance of x sub I with y sub j. Okay. Now, a couple things you might want to note here. Take a look back here at number 2. Take a look at number 2. This gives us an expression for the variance of the sum of these weighted random variables, right? Now, take a look, for example, in this form of that expression. What happens if the x's are independent of each other? Well, what you get is that all these covariances are 0, right? Because when two random variables are independent, it implies that their covariance is 0. So this entire double sum becomes 0. And so what are you left with? Hey, this is really great, right? It says that if you have a collection of random variables, these x's, if all these x's are independent, then the variance of this weighted sum is just the sum of weighted variances, but the weights have to change, right? When you pull you guys did this kind of problem for homework, right? If you have a constant in here times x, the variance of it, when you pull it out, the constant gets squared, okay? So this is pretty nice, though. The variance of the sum is the sum of the variances when the variables are independent, okay? If you happen to have a little constant in here times that variable, then you can pull that constant out, and it gets squared. All right.